I can't see the apple. It's too small and upside down.
Silly Sawhorse, I think you're too far away. Let's take a look at the ray diagram. So the apple you see is too far from the lens. It's past the point labeled 2f, which is twice the distance of the focal point away from the lens. So we'll use an arrow, a black arrow, to represent an object. Let's draw a ray of light coming from the top of an object traveling to the lens. So because this is a convex lens, as it's bent outwards like this, it's two spherical pieces put back to back. Then this ray of light will bend and converge inwards, hence the magnifying glass you're using is called a converging lens. So this top ray of light will bend downwards and travel through the focal point on the other end of the lens. Just about there. We can draw another ray of light coming from the top of the object, which travels from the object's head here again, and it passes through the focal point on the same side of the lens on the left side, and it will bend once it reaches this lens. So once it reaches this end, this beam of light will run parallel to the central axis through the lens. All right, so to find the final size and location of the resultant view of the object, we look at where the two rays of light we drew intersect. They are right here. So as you can see, this object, let's say if we were to draw the resultant object right here, it would be smaller and inside the 2F line on the opposite side of the image. This means the apple you're looking at will be smaller and upside down. So to check this, we can draw another ray of light from the top of the object here through the center of the lens, and it should intersect at the same point. So we could try that. All right, and it should intersect right at that point. So this object will be smaller in height, smaller in absolute height from the central line, and it will be closer than the original object as it's inside 2F rather than outside 2F here. So also the apple you see when it's upside down and too small is called a real image. This is because it is seen through the lens as it appears on the opposite side of the lens. A real image can be seen if a screen or piece of paper were placed there as actual beams of light reach them.
Okay, cool. So I moved closer and it's bigger now, but it's still upside down. What's going on, man?
All right, so let's take a look at the ray diagram again. This time you're still a little bit too far from the lens, so your image now is inside 2F. We can draw a ray of light coming from the top of the object, passing through the converging lens, and it will bend downwards to the focal point. We can do the same thing as the last example, where we draw a line from the top of the image to the focal point on the same side, and it will bend and converge parallel to this. So we can check that drawing the yellow line to the center again, and we can see the image is on the opposite side still. It is bigger now, and it is still inverted. So this is still a real image as it is on the opposite side of the lens. However, it is in fact inverted.
Oh god, I can't see anything now. I'm blind.
Silly Sawhorse, I can assure you you're not actually going blind. So your object is actually at the focal point right now. So if we were to draw a line coming from the top of the object, converging down through the lens to the focal point as usual, we'll have a line going here. And if we were to draw another line going through the focal point on the same side, you would notice it would have to go directly downwards to do that. And then you get a vertical line here. So if you see, these two lines will actually never converge. They'll just keep on going forever. So that means you will not have a resultant image to see.
Oh hey, the apple's big and right side up now. Thanks, Andrew.
All right, so now we can see a larger image that's up right now. So that means you're probably inside the focal point here. We can draw a ray coming from the top of the object through the lens again, and it'll go through the focal point just like it usually does. But we can't draw a line to the focal point here because it has to go backwards, but we can extend the line here. And we can continue that line through the top of the object and through the lens as it will bend parallel to the central axis. So now notice that these two rays never actually converge. We can continue these lines backwards again using dotted lines, and we can see that it meets behind the object. So this object that's resultant is larger and it is upright. However, it is a virtual image. Unlike the other images that were on the opposite side where we can see through the lens, this image cannot be represented by real light. It is just something that we can see with our eyes. So now that we talked about converging lenses like a magnifying glass, we can look at a divergent lens, or in this case, a concave lens, because it's like a cave where light comes in. So in this case, light is spread outwards rather than converging inwards. If we're to draw a ray of light coming from the top of the object to the lens, it will spread upwards, and it will follow the same trajectory as it does coming down to the focal point on the side here. If we were to draw a line coming from the top approaching the focal point on the other side, it will come here and it will bend to be parallel. And as you can see, these lines are still diverging from each other. They will never meet. So if we want to find where the object will actually be, the resultant image, then we can draw these lines back. So we can put a line back there, and we can put a line continuing back here, and we can see that it intersects right here. So now the object is smaller than the original object, and it is upright. And what's interesting about a divergent lens is that the object will always be smaller and always be upright and virtual.
Hey, why am I so small and upside down?
Here we'll use an example of an arrow as placed for you looking into the concave mirror. The reason that this is happening is because you are placed outside of C, or the central point, which is also located at 2F, 2 times the focal point. Again, to draw the ray diagram, we'll start by drawing 2 rays off the top of the arrow. The first being the red line, which will go horizontally from the top into the mirror and then reflect downwards through the focal point. The second starting at the top of the ray, or the top of the image again, going through the focal point first, reflecting into the mirror and going horizontally outwards. As we can see here, the intersection of these points is in the negative real space down below. The intersection is at the top of the new image which is created, which explains why your image is upside down and much smaller than the original.
So now I'm the right size, I'm a little bit bigger, but I'm still upside down.
You appear normal size but are upside down is again due to the ray diagram. Similarly to the first one, we can see that the reflected image is once again in the negative space down below. To draw the ray diagram again, we start at the top of our image and draw the first ray going into the mirror horizontally and down through the focal point. The second ray again starts at the top of our image, goes down through the focal point, reflects off the mirror second, and comes out the side. The intersection of these 2 points is at the top of our new image, which as we can see is down below the first one. As we see here, the reason this occurs is because now we are between the focal point and the central point.
Now I can't see anything. What happened?
The reason that you don't see anything now is because you are directly at the focal point. The ray diagram for this is interesting and shows why you can't see anything in the mirror. Again, starting from the top, we will draw through horizontally into the mirror and then down through the focal point. Secondly, we will draw straight down now from the top of our image through the focal point. As we see, the only intersection occurs at the focal point as the rays diverge from the bottom. Therefore, there's nowhere for the image to begin other than at the focal point and ending also at the focal point, which is why you can't see it.
Okay, there we go. Now I'm right side up and huge. Wow.
You finally appear right side up. The reason for this being is that you have now moved inside of the focal point. From here, the ray diagram gets a little bit more complicated. Again, we'll start here at the top of our arrow. We first draw a line horizontally going into the mirror and draw a point here. Next, we will start at the focal point and draw through this intersection into the virtual space. For our second ray, we'll start at the focal point and draw through the top of our image back into the mirror. Here we draw a point and draw a horizontal line going through it back into the virtual space. Here at this intersection in the virtual space is where the second image will now be shown, and it explains why our image is now right side up in comparison to being between the focal point and the center, or outside of the center, where our image was down below.
Let's do a basic practice problem. If a 10 centimeter tall object is 15 centimeters from a convex lens with a focal length of 20 centimeters, what are the image distance and image size? The first equation we'll use is to determine the image distance, di, and yes, I used a ruler on my laptop screen for this. 1 over the focal distance equals 1 over the object distance plus 1 over the image distance. Plug in the numbers, and voila. To find the image height, know that the ratio of the image and object heights equals the opposite of the ratio of the image and object distances from the lens. A bit of arithmetic, and there's the answer.